Krishna, now speak.
Okay, thank you, sir. So in this particular class, we are going to start enzyme kinetics. Actually, we are starting with an curve. This is a hyperbola given by two scientists. One is this is called curve. So the two scientists, I would like to show you okay, so this was the first one. This is called Leonor Michaelis, along with his partner, Maud Manton. So they too have devised some simple reactions using one enzyme, and this enzyme is very important again. So they use sucrose converting enzyme. So this is called invertase actually, or you simply call it sucrase. So based upon this enzyme kinetics, they have devised an equation, and based upon this equation, they have plotted a curve. So finally, they are able to achieve some simplified version of their curve like this. But before this, they have did many experiments. So they have tried with different concentrations of the substrate. So actually, they have taken different sugar. Here, the sugar they have used was sucrose, because they were converting sucrose into glucose and fructose. So the concentration of the substrate sucrose, 0.2 micromolar, 0.5 micromolar, and 1 micromolar, actually this was the Km value. And they have plotted this curve either below the concentration of Km or above the concentration Km. So, okay, so we will discuss everything. Km also we need to discuss first, then I will come over this plot again. So before starting, I would like to tell you what is Km, what is V maximum, and all these things, so that you better understand this concepts. Okay. So quickly, we are moving to Pathfinder. So actually, this you need to read from here, from the first chapter itself, enzyme kinetics. Enzyme kinetics is the quantitative study of enzyme catalysis. Guys, I hope my voice is very clear and you are able to see the screen. And if you are facing some issue, please let me know so that we can fix it before going into the detail. Ankita is saying all clear. Okay, thank you, Ankita. Then we can move. Okay, so what is enzyme kinetics? Firstly, a question came into our mind why we are saying that we are starting enzyme kinetics from so many days. Actually, what we are going to study in this particular class or in these classes, upcoming classes, is actually how to determine the rate of reaction, how different inhibitors may inhibit the enzyme, and actually we need to discuss many different kinds of inhibitions. So one is competitive, non-competitive, uncompetitive, and it may be a combination of two. So it is called mixed inhibition also. So how substrate is able to bind to the enzyme, and it is able to convert into the enzyme is able to convert the substrate into the product and release the product. So everything we are going to discuss. Also, we will derive some of the equations. So for example, one of the simplest equation called equation, Michaelis-Menten equation, given by these two scientists, as we have seen in the last photographs. So, okay, so before going into the details, let us learn some basics. Okay, so what is enzyme kinetics? Enzyme kinetics is a quantitative study. There are two things. One is qualitative, one is quantitative. It is both the terms are related to statistics. Okay, statics. So here this quantitative mean number. Okay, so if you want to know the number exactly how much concentration of the substrate you exactly require to reach maximal velocity, or to calculate different things, for example, Km. And actually there are two other things, very important terms related to this enzyme kinetics. One is known as turnover number, and second is the specificity constant. We will discuss them also. But actually, what is turnover number? Turnover number we also have discussed in our earlier classes. Turnover number is called kcat. So actually, this is also given over the next page itself. So here, when you go through this text, we will learn what are the significance of calculating these Km and V maximum. And then we will come to two important terms. One is called catalytic constant, or this is called turnover number in simpler words, or we call it kcat. Okay, so this kcat is actually the Vmax divided by total enzyme concentration. So actually this value will give us an, uh, so based upon this value, we can calculate how many substrate molecules are getting converted into the product. So the catalytic constant is the rate of product formation. So what is the product formation? Obviously, the number of substrate molecules are getting converted into the product. So when an enzyme is saturated with the substrate, suppose there is a high concentration of substrate and all the enzymes which are present in the solution, generally the enzyme is present in the solution in very less quantities. We will also discuss that concept. But the substrate, we are supposing it is present generally 5 to 6 order of magnitude, always greater than the enzyme concentration, so that it will saturate all the enzymes. It will bind to all the enzymes which are present in the solution. So this is called the saturated enzymes, okay, with the substrate. So if this is a condition, all the enzymes are saturated with substrate, then the catalytic constant or kcat is indication of rate of product formation, how many substrate are being converted into the product. And actually we count it per second. So the unit is itself per second. So how many substrate molecules are getting converted into the product per second is actually called the kcat value or the catalytic constant. And third term is the turnover number. Okay, so and one more term we will discuss in this text. Actually, this is called specificity constant. Simply, if you divide this kcat value or the turnover number with the km value. So actually, what is km? Km is the substrate concentration at which, so it is the itself substrate concentration at which the reaction velocity is half Vmax. So let us discuss km first. Okay, so km is actually, we have discussed so many times this curve. So suppose this is the maximal velocity an enzyme can approach with the saturated with the substrate. And if you find something in between, this is zero, this is maximal velocity. So in between the two, actually this is called half V maximum. If you draw a perpendicular line like this and then on again and lines with this horizontal line with this y-axis. So the value you got over this axis, over the substrate concentration, so this is called Km or the Michaelis-Menten constant. So if you divide the kcat value or the turnover number with this concentration, you will get another number, another important term that is called as specificity constant. And the other term, you can simply show it like a ratio. This is the kcat divided by km is equivalent to the rate constant for which reaction between the free enzyme and the free substrate. And this is also called specificity constant, okay? And actually here the unit will change, the per mole per second. Actually, we are having a unit because we are dividing this with the substrate concentration, and you know the substrate is actually the molar concentration, and actually this is the lower side. So, and this kcat was having a unit per second. So actually this will be per mole per second. Okay. So I hope you are able to get this. If not, we will come again over this. So we were here. So enzyme kinetics is a quantitative study, not a qualitative study. Here we are dealing with numbers of enzyme catalysis. Kinetics, the kinetic studies measure the reaction rates and the affinity of enzyme and substrate and inhibitors. So the two things we are going to deal, actually first we will learn, we will measure the reaction rates, how fast a reaction can be, and with respect to the substrate concentrations. And second thing is the affinity with which this enzyme will bind either with the substrate or with the inhibitors. So these inhibitors are some substrate analogs, so therefore they are able to occupy those active sites where these substrates are going to bind over the enzyme. Kinetics also provide insight into the reaction mechanism. So the second thing is actually not only this is dealing with the measurement of the reaction rates, this kinetics will also help us to understand how a particular reaction is going on into the molecular mechanism itself. For example, how an inhibitor is able to bind to this enzyme, or whether competitively, uncompetitively, non-competitively and like so on. So the general principle of chemical reaction applies to the enzyme catalyzed reactions as well. Okay, so we know some simple reactions, some chemical reactions, but if we talk in terms of enzymes or in biocatalysts, actually the proteins which are present in living systems, so they are also following the same mechanism. They generally increase the rate of reaction similarly as normal reactions, but actually they increases the rate of reaction several folds so that the reaction can be completed in less time. Okay, so some of the simplified reactions are shown. So how much is the rate of reaction? So some values are given in this table actually. So the catalase is having the maximum turnover number. So the maximum number of, so here is a table. So there are some values of turnover number for some of the enzymes. So here you can see the catalase is having the highest value. So it is something 4 into 10 to power 7. Okay, so this is per second. This is the kcat value or the turnover number. So actually this is the value an enzyme when it is fully saturated with the substrate. So this much number of substrate molecules, it is able to convert into the product per second. So for catalase, it is very high, then followed by carbonic anhydrase and so many enzymes. And you will see the lysozyme is having only 0.5 turnover number. So this is very, very less when we compare with the catalase. Okay, so based upon this, one thing you are able to estimate the reaction rate. Second, you are able to assume what kind of reaction mechanism it is following, and so on. Okay, so suppose there is a simple reaction, simple chemical reaction. This A plus B is getting converted into a product P. So these two will be set to substrates. So there is a query actually, I do not know what is this. How to calculate the total enzyme concentration. We are not calculating the total enzyme concentration. Actually, it is the enzyme concentration which is present in our test tube before adding the substrate actually. Okay. So this ET is the total enzyme concentration. So I will tell you this also. We are coming to this portion. Okay, Ankita. Have patience. So suppose there is a simple reaction, two substrates, one substrate is called A, second substrate is called B. So they are getting converted into the product. This is a simple chemical reaction. Suppose there is no enzyme. So P is the product and these two are reactants, or simply we call them substrates. Rate of reaction can be expressed in terms of either the rate of disappearance of, now if you want to show the rate of reaction, so you can assume two things, because both A and B are will be disappeared when this reaction will take place, and both will combine to make a product P. So this is either, there are two ways to write a reaction rate. Either it is a rate of disappearance of one of the reactants. So one of the reactants in the sense either A or B, and actually both will disappear as the product will form, or the rate of appearance. So you have two terms, one is disappearing, one is appearing. So obviously the reactants or the substrate will disappear and the product will appear in the reaction and the reaction will proceed. So the rate of disappearance will be given by this negative value. So this negative value is showing nothing, but this is the disappearance, because the concentration of A and B will becoming less as concentration of product will increasing. Okay. Similarly, okay, so and this change is with the time actually. So concentration change of A, and this del is a small change actually, because the substrate is present in very large amounts. Okay, so if you are not able to understand this from here, you may go to the reference called Leninger. Okay, so this Leninger is also saying the same thing actually. So see here. So suppose there is a reaction, in vitro reaction. In the test tube, we are doing a reaction. We are adding the enzyme and substrate, and we are looking for some color change or some product formation, for example. Okay, so the initial rate will be V0 or V0. And in a typical reaction, enzyme may be present in the nanomolar quantities. So suppose in the test tube you are having an enzyme. You know enzymes are present in a very less concentrations in the living systems. So generally they are present in nanomolar or something, some less quantities, some lower values. Whereas you add substrate, which is generally 5 to 6 orders of magnitude higher than the concentration of enzyme itself. Now you can assume this enzyme will be saturated with substrate because all the enzymes active sites will be having bound substrate because substrate is present already in higher concentration, 5 to 6 order of magnitudes higher at least, or it can be even higher. Okay, so when this is happening, when the reaction is happening, so it is only in the beginning of the reaction is monitored over a period of time in which only small percentage is of the available substrate is converted to the product. So delta S, or the change concentration of the substrate, can be regarded as constant. What this mean? This mean that because the substrate was present in higher concentration when compared to the enzyme itself, therefore with the time it is assumed that there is no change in the concentration of substrate because it is almost constant, meaning there is very less substrate or reactant is consumed in the reaction to be converted into the product in small time. So now we are moving back to this. So here you can see this. If the disappearance of A is happening, so A is a reactant. Okay, so this substrate or reactant is shown by there is a small change del. This delta is showing a small change in concentration of A with respect to small change in time. Okay, where this is a change actually. Now this concentration of A is actually given in moles per liter or simply in the molar concentration, capital M. And T is the time, generally taken in seconds. Okay, so likewise, the rate of disappearance of B. Now we similarly, as we have calculated for A, we can also calculate for B. So because B is also a substrate, so this will disappear with time. So there is a minus sign, small change in concentration of B upon divided by del T, because this is a small change in time. With time, there is a change in concentration of B and it will decrease. So there is a negative sign. And the rate of appearance of product. Now product will be found in the reaction. So therefore the concentration of product will increase. So similarly, we will put a positive sign here or positive sign because there is no negative signs. Okay, so this change in concentration of product with time is generally a positive value. So therefore they, they have written this, okay, del P divided by del T. So now if you find the rate of reaction, you can put all the things together. There is a decrease in concentration of A, therefore they will put a negative sign. There is a decrease in concentration of B with time, so they put a negative sign. And there is an increase in product concentration with the time, so therefore it is a positive value. Now, one more thing is when you are given with some values of concentration, so you will put them as powers. Okay, for suppose you are having here F moles of A and G moles of B are getting converted into the product, then how you will write the rate of reaction? Then you will put those values which are present before A or B as their concentration powers, simply. So the rate of reaction at a given time is proportional to the product of the concentration of the reactant raised to the appropriate power. So there are two substrates. So you will raise their powers as the values which are uh, before A or B. So the rate is directly proportional. If you remove this proportional sign, so is equal to, so you will put a value K. This is a proportionality constant, and this is actually called the rate constant K. Okay, I hope this is clear up to here, and because there is no such hard calculations, they are simply representing the rate of reaction either with these values or they are putting the powers of these reactant concentrations. and they have added some proportionality constant that is called the rate constant K. And these F and G are called exponents, must be determined experimentally. So you need to do some experiment. You need to take the enzyme and substrate in the test tube to determine the values of F and G. So they are not necessarily equal to the coefficients of the balanced equation. Same thing is the exponents in the rate equation are usually small. Whole numbers, for example, either 1 or 2, okay, 1, 2 or 3, they are generally the less numbers, whole numbers. In some cases, this is also possible that the value is equal to 0. Okay, so the small values, the values of the exponent are related to the number of molecules which are involved in the detailed step that is constituting this mechanism of the reaction. If you need to calculate the overall order of the reaction, so what will you do? You will simply sum all the exponents. So you will add these values. So, okay, based upon these values, you are able to calculate the rate overall order of the reaction actually. So what is the order of reaction? Let us calculate the order of the reaction. Suppose there is a reaction. So here you are having only one substrate. So suppose there is a substrate A and it is getting converted into product. I'm writing this equation. So this is the substrate, and suppose it is getting converted into the P product. So what will you write? The rate of reaction will simply is the concentration, because this is 1. So you will put this one as power of this, and you will remove the proportionality constant, and you will put a value, a constant K here. Okay. So it's very simple. Then again, if you're having two products, suppose there are two substrates, A and B are getting converted into two products, C plus D. So you will put these values as 1 and 1 here, and simply you will add a proportionality constant here. So K is the proportionality constant. These are substrate concentrations, right? Now, if you need to kindly mute yourself, actually this is disturbing us. So, okay, so I do not know who is. Okay, so now if you need to calculate the overall order of the reaction, so in some question they actually have asked for what will be the overall order of the reaction. So how you will calculate, you simply add these values. Okay, so because here this K is called the rate constant, exponent of the concentration A is 1 and the exponent of concentration B is also 1. So then the reaction is said to be a first order reaction with respect to either A or with respect to either B. But if you are going to calculate the overall reaction, then it will be second order, okay? Because there are two substrates involved in this reaction. Therefore, if you add 1 plus 1, it will be 2. So it will be a second order reaction overall. So whenever a question has been asked, you need to look over the question very carefully, whether he is asking in terms of A, in terms of B, or in terms of overall reaction. Okay. So if he is asking for overall reaction, it will be a second order reaction. Otherwise, it will be a first order reaction. Okay. Many common reactions are either first order or second order. So mostly the reactions are either first or second order. But we will also look for some zero order reactions, as the Michaelis-Menten equation or the curve, which is a hyperbola, also showing some zero order reactions. Okay. So the possibility exists that the exponent of the rate equation may be equal to 0. If it is so, so the rate of reaction, suppose this is a reaction A is getting converted into the product B, given by the equation. So there is some equation, if suppose there is a rate equation is equal to 0. So you will simply put this 0 as power of A. So A into A, this is the concentration of A and the power is 0. And now this value will become 1 because power to someone is actually equal to 1. And when you multiply 1 with K, it will be equal to K. So this will be equal to simply your rate constant K. Okay, so for a zero order reaction, the rate of a reaction is simply represented by this value K, which is also the rate constant or the proportionality constant. Such a reaction is called zero order reaction, and its rate, which is a constant, actually constant is K. does not depend upon the concentration of reactant. So therefore, in such reactions, when the reaction is zero order, you need to underline this. It is not going to be affected by the concentration of reactant, because it is not depending upon the reactant concentration, because this reactant concentration to the power 0 is equal to 1. So it is not going to affect the rate of this particular reaction if the reaction is zero order. But depends upon the other factors, where such as the presence of catalyst or the enzyme itself. So presence of catalyst, for example, some other factors like pH, temperature, these factors will affect the rate of reaction. But this is very important, that all the reaction will be affected by the substrate concentration, but zero order reactions will not be affected by the substrate concentration itself. Okay. If this is not clear, let me show you something else. Okay, so here also it is given. Suppose there is a reaction. Okay. So simply what this curve is showing us, suppose you are having different substrate concentration, these dark lines. So this is substrate concentration is 0.2 micromolar. Here you are having 0.5 micromolar, and here you are having 1 micromolar. So if you are having some other value, it will come like this, okay, here. So you can see that the rate of reaction or the curve is overall changing when you are changing this substrate concentration, because mostly these type of reactions are either first order reaction or second order reaction. Therefore, they are affected by the substrate concentration or the reactant concentration itself. But when we are talking in terms of a zero order reaction, it will not be affected by the substrate concentration. So suppose this is actually called the Michaelis-Menten curve. So in this curve, there are three components. If you look here, this box, okay, so this is actually showing the half Vmax value here. And if you draw a perpendicular line, you will get a value that is called the substrate concentration, at which your enzyme is having half maximal velocity. So this is called Km value or Michaelis-Menten constant. Okay. Actually, this is the substrate concentration itself. Many times the direct question can be asked, what is the Km? So it is actually the substrate concentration. And generally it is represented in the terms of millimole. Okay. Now there are three components of this curve. If you are looking, this is a simple, if you look here, this is a 0. So let me annotate this so that you are better able to get something. So this is a value here, this is 0. Sorry. Okay, so if you increasing the substrate concentration, suppose this is the substrate concentration over x-axis, you are increasing this way. So you will able to see this is the rate of reaction. So this is V. So with increasing the small concentration of the substrate, there is a big increase in the velocity of a reaction up to here. Okay, so actually what kind of reaction this is, if you are able to correlate this is the first order reaction. Okay, so this will be your first order reaction. What will happen when all the enzymes will be saturated with substrate? Then you assume there is a small increase with increased. So here you can write this is a first order reaction, first order. Actually, it is hard to write like this. Let me. So fine. So this is first order reaction. Then you're having this part actually up to here. So from here up to here. Okay, so let me conclude this. And up to here actually. Then from here to here, this is the third part of this same curve. So actually this is a hyperbola. You also need to remember this is a hyperbola, somewhere it is given actually. Okay. Then this is the first order kinetics. It is showing the first order kinetics. Here it is showing no change. If you increase the substrate concentration very, very much, then there is very little change in the this velocity, and actually this will follow this trend. So this will be like this if you extrapolate this. So let me take a black so this will something like this. So from here, and if you go beyond, so this is actually called the zero order rate kinetics. So here you can write zero order. But if you look here, it is a kind of means it is not increasing very much. It is there is a small change, and it is steadily increasing with the increasing substrate concentration up to here, or even up to here. So this is actually called the mixed. Okay, so you can write mixed kinetics here. And what is the overall shape of this curve? This is called hyperbola. So you also need to remember this, because this may be a direct question in any examination. Hyperbola. So this hyperbola is having three different segments, where it is showing first order reaction kinetics, where it is showing zero order reaction kinetics, and also a mixed reaction kinetics, means not either one or zero. Okay, so there is a query. Let me quickly look into the query. What is your problem? Okay, so what is the concentration of catalyst in this graph? Okay, so mostly when this equation is plotted, or when you are looking for such kind of curve, okay, so there is no exact concentration we are taking. Generally, we are assuming that the concentration of substrate is very, very high than the concentration of enzyme itself. So if you are able to see here, Ankita, this is also given here. You are assuming the substrate concentration is very, very much in comparison to enzyme. So that this enzyme is showing first order reaction kinetics, because suppose there is a test tube in your hand, you are adding some enzyme here. So here is an enzyme. So simply I'm writing like E, okay, up to here. And then you add at time, you are taking some value, and at some time you are adding the substrate to this same test tube. Now you are adding the substrate concentration much higher than this enzyme which is present in the test tube. Okay, so when you're adding the substrate to the enzyme solution, you are taking this point, this time point as zero. Okay, now suppose it is like you will leave it for the reaction, but suppose if you take a stand, this pipette stand, and you will add some kind of pipette here, so that if you add substrate dropwise in this particular test tube, so what will happen, the concentration, the substrate concentration will be increasing. Okay, increasing with the increasing substrate concentration initially, these substrate enzymes, these substrate molecules will occupy all the binding sites over these enzyme molecules, so that they all will be saturated. So you can assume this point up to here as first order rate kinetics, because with the increasing substrate concentration, because all enzymes are free, and as soon as the substrate will reach to the enzyme, they will bind over enzyme active site. Therefore, the rate of reaction is very, very uh, much directly proportional. So if you're increasing the substrate concentration, the velocity will increase. But after some time, what will happen, if you're increasing the substrate concentration beyond the level of this enzyme concentration which is present in the test tube, so what will happen, the enzyme is not free now, so it is not going to affect your rate of reaction very much. And ultimately this is zero order rate kinetics, where your there is a rate increase in rate of reaction is very negligible with increasing substrate concentration over this x-axis. I hope this is clear, and if you are having some doubts, uh, yeah, enzyme concentration is constant. At least you will take one constant. Now, otherwise it will complete mess. So you are taking the enzyme constant, and you are so the one variable, the enzyme concentration is constant, and the other variable, so this substrate concentration is variable actually. So this will change, and you are looking for the change in velocity, so rate of reaction. And you are, if you are able to see this, it is never approaching this Vmax. Okay, so this will always remain something below this particular line. So this is V maximum actually. So this is actually the Vmax we are assuming, but this is a living system, and in a living system nothing is 100%. So the V maximum, the assumed V maximum will never be approached, and the value of V maximum is always less than this assumed value. Fine. So, okay, we are coming back to the discussion where we have left actually. So that's how you are able to calculate. So actually we are going to discuss this Michaelis-Menten curve. Therefore, I told you that actually this curve is itself made up of three components. So this is actually the portion. This hyperbola can be divided into three portions. This is the first order rate kinetics. This is the zero order rate kinetics, and this is a combination of these two. So this is mixed type. So in many examinations, they can also put some values like. Simply, they can put values like A, B, and C over this curve, and they may ask, so what kind of reaction kinetics it is showing. So suppose this is A, this is B, and this is C. So you must be aware that what kind of reaction kinetics it is showing. Okay, fine. So we have discussed this actually now. Kinetics of enzyme catalyzed reactions. A particular useful model for the kinetics of enzyme catalyzed reaction was devised in 1913 actually by two scientists, Leonard Michaelis and Maud Manton, as we have seen in our reference book. Okay, so actually they are here. This is Manton and Michaelis. So in 1913, they have calculated some values, and based upon those values, they draw some curves. And actually, one of the famous curve they are able to get is actually called the curve, Michaelis-Menten curve, and they also give some equation that is called Michaelis-Menten equation. So we will see how they have calculated these values. But before that, they have assumed something. So some assumptions, three major assumptions of this enzyme kinetics. So this is actually called the Michaelis-Menten equation. So according to Michaelis-Menten equation, the equation saying the V naught, or the initial velocity, is equal to V max, the maximum velocity one enzyme can approach, multiplied by the substrate concentration. So V max into substrate concentration divided by Km plus substrate concentration. So Km is itself the substrate concentration. If you add this Km plus substrate concentration is a kind of total substrate concentration. So somewhere when the Km value is very, very less, we have also discussed the low Km enzymes and high Km enzymes. Okay, so when the Km value is very, very less, sometimes we can neglect this, and then if you neglect the Km, this will become zero, and the substrate concentration can cancel this value. So therefore, in those cases when the Km is very, very less, so the initial velocity is equal to V maximum. So we will also see for three possibilities of the rate of reaction. If this Km value is less than Km, if this Km value is equal to Km, or it is greater than Km. So there are three possibilities based upon which, if this Km value is changing, the overall shape of this equation and the curve will change. Okay. And actually, all the calculations which they were using, they were doing, Michaelis and Manton. So they are based upon this Briggs and Haldane, they give some kind of explanation to their assumptions, their theories. So in 1925, they gave some model that is called steady state model. We will also look into the steady state. What is this? And actually, so let us go into the Pathfinder itself. So there they have better explained everything. So the two scientists have devised in 1913 this particular kinetics and this kinetic model when they were studied the reaction in which the enzyme invertase. So this enzyme is important. So you need to underline some of the very important points. So for example, one is this enzyme invertase itself. This is also called sucrase. Right here. So which hydrolyzes the sucrose itself. And sucrose, you know, this is a disaccharide, and if it is hydrolyzed, it will be broken down into the two monosaccharides. One is called glucose, other is called fructose. Sometimes it is called the invertase sugar. Okay, invertase. So invertase, because overall this glucose is having some positive value, fructose is having negative value. So it will lead to the change in the polarization of those sugars. So you are having two. So it will lead to the invert of the values actually. So actually, I'm not here. I'm not having a model actually. So let me explain what is invertase actually first, then we will move next. Okay. Hope this you have studied in your BSc first year, so I need not tell you, but I do not know how many of you are aware why this is called invertase. So let me quickly give you one example. If you write invert sugar, you will find some very interesting things. Okay, so why this is called invert sugar. Wait a minute, actually I'm finding some better examples so that I can explain this topic to you. So exact number they have not given here actually, so this is a problem. Okay, no worries. So I'm sharing one more screen. See. So if this sucrose, which is a disaccharide, will be broken down into the glucose and fructose. So this glucose which is formed is actually a dextrose. What is dextrose? Dextrose will rotate your plane of polarized light towards your right hand side. But this fructose, which is having a higher value, so it will be levorotatory. So it will rotate the plane of polarized light towards left hand side. Therefore, because this value is large, actually they have not shown the values here, but I hope this is having some value minus 119. I think it's actually not showing in this. So therefore, sorry, this is minus 92. Okay, so this is having some value minus 92, and let me annotate fast. Minus 92 degree. So this will rotate your plane of polarized light towards left hand side, because this is levorotatory L, and therefore this will be a greater value. And this dextrorotatory value is less, which is rotation. The optical rotation is plus value because it is right hand side. So therefore we are writing plus. This is 52.7 degrees. Okay. So therefore, this is called invert sugar when this is broken down. The sucrose is hydrolyzed because the sucrose itself have plus value. This is also dextrorotatory, 66.5. So it is also these values, actually I forgot those values actually, but these values are given over page number 85 in your book, first chapter, first part. Okay, so if you go to 7th edition, page number 85, they are given the hydrolysis of sucrose. So see here, because this is a positive value, and this therefore this is dextrorotatory, and this is sucrose. But when it is hydrolyzed by this particular enzyme invertase, it will be converted into, if you add this, this will be a negative value, greater negative value. So it will be overall levorotatory. It will rotate your plane of polarized light towards left hand side. So dextrose sugar is getting converted into levorotatory form. Therefore, it is called invert sugar. And actually, this particular reaction in the presence of water and this enzyme, this was studied by these two scientists, Michaelis and Manton, and based on this reaction, they have devised this uh, kinetic model. Okay, fine. We then move back to our okay. So now this kinetics of enzyme catalyzed reaction we were discussing, and we have discussed this, that this invertase is hydrolyzing sucrose into two, either glucose and fructose. So this glucose is dextrorotatory, fructose is levorotatory, and this is having greater value, minus 92. Therefore, overall, this will lead to the formation of invert sugar. Michaelis Menten described the relationship between the reaction velocity and substrate concentration. Now, because the equation that is called the V naught is equal to V max into substrate concentration divided by Km plus substrate concentration. Actually, this is a relationship between the reaction velocity and the substrate concentration itself. To explain the results in the conversion of sucrose into glucose and fructose by the enzyme invertase or sucrase, Michaelis-Menten proposed the following scheme of the reaction. So what scheme they have proposed, they told that the sucrose is the substrate. So sucrose, either substrate or S. So it will bind with the enzyme invertase. Okay, so it is showing some kind of reversible reaction, and it will make the enzyme substrate product. So the rate of reaction of this reversible reaction will be given by K1 and K minus 1 if it is a forward or a reverse reaction. Okay, so K1 or K minus 1. If it's going this way, this is K minus 1. If it's going forward, this is K1. And it is mostly seen that the second reaction will not be a reversible reaction. Mostly it will unidirectional reaction, and this enzyme substrate concentration once formed, it will lead to the release of product. And okay, so one more thing you need to know here, it is not necessary that this enzyme and product will not be converted into the enzyme and substrate, but it is very less likely that it will be converted back into the enzyme substrate complex. Once the product is formed, there are so many changes in the substrate itself, so that it will lead to the formation of product itself. And if it is so, and mostly it will not go back in this way. Therefore, there is only one rate constant, that is called K2. Now, these three values, K1, K minus 1, and K2, are going to help us in the whole enzyme kinetics. So in this equation, this K1 is the rate constant of the formation of this complex from the enzyme and the substrate. We know K minus 1 is the rate constant for the reverse reaction. This also we had discussed. The dissociation of this ES complex is given by K2. K2 is the rate constant for the conversion of enzyme substrate complex to the product and subsequent release of the product from the enzyme. Now, according to the MM approach, when rate that is called the velocity of the reaction of the enzyme catalyzed reaction is measured at a varying substrate concentration, the rate depends upon the substrate concentration itself, as we have seen also from one earlier curve actually. So sorry, from there we have seen that, okay, so this is clearly showing that the rate of reaction or this curve is completely depending upon the substrate concentration, because before deriving their final curve, they also check that whether the substrate is going to affect the enzyme kinetics or enzyme rate of reaction or not. Okay, so it is changing. So therefore, the rate depend upon the substrate concentration. Obviously, at a relatively low concentration of substrate, that is called initial velocity V naught, increases almost linearly with an increase in the substrate concentration. So this is a very linear relationship. It is very directly proportional relationship. So the reaction reaches a maximum velocity that is called Vmax, approaching this with an increase in the substrate concentration. Okay, so this concentration is already there in the test tube. So more and more number of substrate are binding with the enzyme itself, and therefore the rate of reaction is increasing. So the substrate concentration is increasing, and it does not increase any further by increasing the concentration of substrate. Therefore, this is called the saturation effect. Means the saturation effect is a kind of effect when all the enzymes are bound with substrate already. So there is no free active site to bound with more substrate molecule. Therefore, the rate of reaction then will not increase further. Okay, fine, no problem. Actually, you have this much. You need to remember. Actually, you need to revise this one, all this much in this today's class. Rest we will discuss tomorrow. Actually, this is complex, so we will move very slowly in this particular section. I'm not going to move very fast. If you are having any queries, please ask. Otherwise, we are ending this class. Yeah, queries are welcome. Please ask your queries if you have. Nikita is having no queries, so I think she is able to understand something. So if you are not having any queries, then let's conclude this class. So today we have started with enzyme kinetics. Then we have discussed some zero order, first order, second order, and mixed kinetics of the reactions. And then we will derive some equations. We will read about some assumptions. And that's how we will move through this topic. And this is the core of enzyme kinetics, is the core of enzymology. This is very easy to understand if you are having very good concept of enzyme and proteins. And if you know about the three-dimensional structure of proteins and enzymes, then it is easy to understand actually. There is no rocket science in enzyme kinetics. This is easy. Okay, so that's all for today. We will meet tomorrow. Okay, thank you. Good night.